We are now going to take a look at polynomial long division, especially with regards to its connection to rational functions. So far, we've looked at rational functions of linear divided by linear. That's in standard level as well. And then linear divided by a quadratic, where we use partial fraction decomposition. And now we're going to look at when we have a quadratic divided by a linear. And the strategy is actually going to work for any kind of polynomial divided by a polynomial of a smaller degree. So we'll look at a little bit of both today because we will need it for other topics going forward. For doing this polynomial long division, it's going to be helpful if you remember how to do just long division in general with regular old numbers that you learned in elementary school, where you have like 1,723 divided by 5, and you get this quotient of 344. And a very quick overview, if you forget, this would be what we're dividing by, the divisor, or in the denominator. This would be the numerator if we had it as a fraction, which is kind of nice to think about for our polynomial or for our rational functions. And then you just say, does 5 go into 1? No. How many times does it go into 17? 3 times. Multiply, subtract, and bring down. And then you just keep repeating that process. So let's take a look at this rational function where we have a quadratic divided by a linear. And I'm going to write it in that same style, so negative 24x squared minus 19x plus 120 divided by 3x plus 8. And if this is divisible by 3x plus 8, you could have also just factored it into having this as a factor, but these numbers are really big, it's really messy, maybe you don't quite get to it, and if we already know one of the factors, this is a nice, easier method of doing it. It also works even if it isn't perfectly divisible, as you'll see in a second. So in this case, what we're going to do is we're just going to look at the first term, the highest power of our divisor, and look at what it goes into in each of our terms of the polynomial. So starting with the first one, 3x goes into negative 24x squared, negative 8x times. And since that's just a term in x, I'm going to put it above the term in x, negative 8x. Right above here, not above this, even though we put it into the negative 24x squared. Alignment is really important here. So now we multiply by the whole term here. Negative 8x times 3x plus 8 is negative 24x squared minus 64x. And then we want to subtract this whole thing. So a similar process to what we were doing before. These cancel out. And we have negative 19x plus 64, so positive 45x. And then we bring down. This bringing down will matter more in a second, unlike it does in regular simple number division. So 3x goes into 45x. Okay, that goes in 15 times. 15 times 3x is 45x plus an 8 times 15 is going to be 120. This is nice, so it goes in perfectly. Because now when we subtract, we get 0, we have nothing left. So there's our quotient. That means if I divide negative 24x squared minus 19x plus 120 by 3x plus 8, I get negative 8x plus 15. Okay, when we look at rational functions, we'll look at the difference slightly and how that pertains to the graph, and not all that long, but here you have the division that you'll need to know in order to do this. Here's a slightly more complicated example. As it pertains to this function, we're not going to have to look at quadratic functions in any of these, but it's a good skill to know, and it applies the same way, and sometimes the more complicated it gets, the easier it is to see the patterns. So we'll take a look at it here as well. Again, we're only going to look for the division at the first term of the divisor and put it into each of these, multiply, subtract, and bring down. So x goes into x to the 4th, x cubed times, multiply all the way through, and subtract. Okay, bring down. X goes into 2x cubed, 2x times, 2x squared times, and then we have 2x cubed plus plus 10x squared. And then we subtract. Minus 7x squared. And now we can bring down. That goes in to this term here, negative 7x times. And then negative 7x squared. We should keep getting the same thing here. Minus 35x. And then we add 11x, bring down, plus 55. X goes into this 11 times. And then we get 11x plus 55. And that gives us 0, so a remainder of 0. Again, because of this division and the domain issue, it won't exactly be this, but we'll look at how this long division pertains to the rational function and its relationship in the next class. Sometimes, though, it won't be perfectly divisible. Sometimes you'll have a remainder. Okay, so if you put this in here, we're going to do the division the same way. I couldn't find that notation on my computer. 2x goes into 2x squared, just 1x time. Bring down. Excuse me, that was not right. Don't bring down yet x. We want this to be an x. Subtract. Nothing. And then we have just 8x. Bring down. That goes in. Ooh, it's the same thing, but it should be above here. There we go. Bringing down here. 2x goes into 8x plus 4. Now we have 8x plus 4. And you'll see that this isn't a perfect divisor, so it's not factorable by this. It might not be factorable by anything, but this means we have a remainder of 1. And if you do think back to how that works with dividing by 7, for example, or any real number, you would say, well, that's 1/7 left. So we could actually say that that is then the remainder. And if you did write this out, again, thinking about the relationship between division and multiplication, you could say that this times this plus this remainder of 1 over 2x plus 1 is 2x squared plus 9x plus 5 equals x plus 4, 2x plus 1 plus just the 1 divided by our divisor. Okay. So same thing, we just get this remainder. Here's our quotient, and that may happen as well, and we will take a look at those too.